Good morning. My name is Kimberly Pierce-Dobson, Business Development Manager for TBC-Brinadd. I'm here with VP of Technology, Mark Luyster, and our Product Line Manager, Kim Tresco, in our last session of our Technology Webinar Series. We've really enjoyed bringing you our information the last 2 months, every Thursday. We've have a lot of exciting things to share, and we love telling you a little bit more about our product, technology, and our service offerings. This presentation is over our Breake systems. They are our polymer breakers for stimulation and drilling applications. All of our products and systems that we've been reviewing over the last several weeks can be broken or a decrease in viscosity with our Breake systems. If you have any questions or comments, you can post them in the comment section or post them below in the questions. We will answer at the end of the presentation. If you are registered, you will also catch the replay via email. All of our replays will also be listed on our website at tbc-brinadd.com. All right, the floor is yours, Mark.
Thanks, Kimberly. So just as a preference to oxidizers, the next 2 slides are a compressed version of our AADE paper. That's AADE-20-FTCE-114, and that was published in April this year at the Fluids Conference. So almost every practical oxidizer product in chemistry has been utilized in the oil field within the realm of judicious health, safety, and environmental practices. Just an example, this is accomplished whereby a selected oxidizer, let's use persulfate, a peroxide, or hypochlorite, is incorporated into a fluid and is used in, for example, fracking fluids. It could be a component of a drilling fluid. It could be post-spotted as a component of a stimulation or a breaker fluid, and it can even be used to break viscosified fluids for reuse. The former, where the selected oxidizer is pre-formulated into a system as a solid, and the reaction is delayed for a period of time. So consider that hypochlorite is more commonly used versus hydrogen peroxide, where the latter is a very effective oxidizer. However, it's increasingly dangerous when handling the concentrations greater than 20%, even 15% by weight. So using the table and the arrow on the left side, you'll find ozone, one of the strongest oxidizers with respect to its measured oxidation potential, as is chlorine and chlorine dioxide. However, their subsequent reactions, especially with organic material, yields very fast and violent reaction. In contrast, when aqueous solutions such as surface water are incorporated with air, the concentration of oxidizing and reducing materials is so low where the oxidation reduction or the redox reactions are extremely slow and they're consumed in their entirety. So using the table again, look at the arrow on the right side. And to further, I'm going to contrast nearly instantaneous reactions, as I mentioned before, with slow reactions, such as lime and carbon dioxide. This dictates a preference for a relatively strong reductant and weak oxidizer, albeit non-combustible, where a reaction is preferably controlled and delayed. So looking at the table in its entirety and comparing the values for the half-cell reactions, note that magnesium, calcium, and lithium are relatively strong reducers as they readily donate electrons. These are typically inorganic peroxides, with the latter a hypochlorite, and they're all commercially available. So continuing with these species, the commercial forms of magnesium and calcium are attractive with respect to cost, and again, relatively strong reducers, the potential to accelerate, thus control the reaction, as well as impart relatively safe handling and logistics. But one important parameter is its relatively slow solubility of this class of peroxides. They remain stable for extended periods of time while in an alkaline environment. So as an example, and we'll use the figure from top to bottom. So a moderate strength acid is used as an external catalyst to initiate the aforementioned reaction with either the magnesium or the calcium peroxide. The target could be the peroxides in a frac fluid, or it's embedded in a residual filter cake. This initiates the reaction as shown, whereby hydrogen peroxide forms, as shown in the equation, and the hydrogen peroxide is produced is much less stable than the magnesium peroxide from which it was formed. As such, it will begin to decompose rapidly to O2. Subsequently, this species hydrolyzes the acetyl linkage found in natural polysaccharides. This results in smaller fragments, and it solubilizes these. In this cleavage, this exposed, it's the aldehyde and the ketone groups, whereby further oxidation of these groups exposes the next site on the glucose ring. And as shown by the arrow, the process simply repeats until the glucose backbone is destroyed. Thus, solid peroxides decompose to form hydrogen peroxide, a very effective species for degrading natural polysaccharides. So our product line includes fine powders, granulated and liquid suspensions of magnesium and calcium peroxide. All are prepared and quality controlled at our manufacturing facility as per our ISO system. They can be packaged in 25 kg, 50-pound fiber board containers, as well as vented totes. These various phases and sizes provide flexibility for application in stimulation, drilling, and cleanup. To further, this table shows these oxidizers can be further divided as the first row shows 3 versions of calcium peroxide. In the second row are the reduced assay versions, and in the third row we have 2 versions of magnesium peroxide. These 7 forms of peroxide provide flexibility for applications in completion, drilling, workover, and fracturing fluids. Just as a quick look, this next table displays a few of the intrinsic differences. So for example, the active concentration varies from approximately 30 to 75%. The available oxygen varies from 7 to 16%, whereby the latter can provide effective breaks even in very viscous fluids. As solids, these provide the ability to encapsulate, and in liquid form, the peroxide is homogeneously distributed. Magnesium and calcium are also available as reduced assay, designated with the R, thus classified as a non-oxidizer when transporting. So next, Kim will describe in more detail the performance that these products afford and expand upon their utilization for PAM viscosified fluids, as well as fluids that are viscosified with biopolymers, such as drilling and workover fluids, and their subsequent degradation versus time. So Kim?
Thank you, Mark. As Mark mentioned, today we will be presenting each polymer breaker's features and performance in various drilling and stimulation applications to showcase the diversity of TBC-Brinadd's brake system additives. We would like to start with our Breake C and CG products. This peroxide series has the highest peroxide content with active oxygen level as high as 16%. The CG product is our granular product, and it was produced or developed for concerns with dust hazard to be reduced in the field. It does remain, both brake products remain stable within storage and has active oxygen loss less than 1% per year. It will disperse readily in water and brines. pHs, when introduced, will range from approximately 8 to nearly 13, it's dependent upon concentration. Typical temperature application ranges for the Breake C and CG is from 100 to 200 degrees F, and typical concentration ranges from 0.25 to 2 pounds per 1,000 gallons. Next, we will look at the performance of Breake C in a Slickwater fluid testing. This testing was presented in our AAD publication that Mark mentioned. The testing shown in the graphs assess the effectiveness of the peroxides to degrade an anionic high molecular weight polyacrylamide slickwater fluid with respect to time and temperature. While generally simulating field operations, we had temperatures ranging from 125 to 225 degrees F. When catalysts were introduced were deemed applicable, the Slickwater base used was either a freshwater or 10,000 TDS level brine. This assessment utilized a Grace M5600 rheometer to capture viscosity under pressure and temperature, whereby an arbitrary timeline was utilized to simulate a pumping fracturing operation. The laboratory method involved the preparation and mixing of a slickwater fluid, such as utilized in fracturing operations, at a dosage as applied in operations where a relatively elevated viscosity is required, for example, like the toe of the completion. Elevated viscosity was utilized in order to determine the degradation of the residual slickwater fluids, thus the necessity to utilize a higher polyacrylamide concentration. This series of testing utilized either a 4 or 6 GPT concentration level. The testing you're looking at now incorporated 6 GPT. The preparation of these slickwater fluids were sheared at 1,000 RPMs for 30 seconds to produce the slickwater. An additional 10 seconds of mixing was used for the addition of a catalyst where necessary. Next, the pre-mixed slickwater was placed into the rheometer cup and a 400 PSI was applied. The total test timeline was approximately 105 minutes. Looking at the graphs from left to right, the following stages were performed. Stage 1 was 5 minutes, where we established initial viscosity at temperature and pressure to compare the final viscosity at shear rate of 511 reciprocal seconds, simulating pumping. Stage 2 was a 30-minute time frame where we decreased the shear rate to 40 reciprocal seconds to simulate velocity in a fracture. Stage 3 was a 60-minute time period where we allowed the slick water to static age at temperature and pressure, simulating shut-in time. Stage 4 was 10 minutes where we increased the shear rate to 511 reciprocal seconds and measured the subsequent final viscosity for comparison. The graph on your left is performance at 125 F, where Breake C at a reduced concentration than the other breakers effectively decreased the viscosity, realizing approximately 10% better performance. Performance on the graph on the right was done at 150 degrees F. The viscosity profile of the slickwater fluid with 1 pound per 1,000 gallons of Breake C at 40 reciprocal seconds is lower than the other fluids, but maintains viscosity during the 30 minutes. After the shut-in period, Breake C exhibited 60% less viscosity than the other slickwater breaker fluids, which had a total of 2 pounds per 1,000 gallon usage concentrations. Next, we will look at Breake C's performance in a cross-linked fluid. The guar setup is a 25 pound per 1,000 gallon guar at a pH of 11.8, the 200 degrees Fahrenheit, and the Breake C concentration was 2 pounds per 1,000 gallons. Looking at this, for viscosity reduction occurs over time and measured until viscosity is at or below our target point of 10 centipoise. Next, we will introduce you to our liquid suspension Breake CL. Breake CL is our calcium peroxide suspension and an environmentally friendly synthetic fluid. It is available at 1 or 2 pounds per gallon concentrations, and it disperses readily into water and brines. The same typical temperature application applies here, from 200 down to 100 degrees Fahrenheit. Typical concentration ranges depending on the application. In drilling, it is 0.5 to 2 gallons per barrel. For stimulation, it's 1 to 5 gallons per 1,000 gallons. Breake CL's performance in cross-linked fluid, it's a 25 pound guar again at 200 degrees Fahrenheit. The Breake CL's concentration is 2 gallons per 1,000 gallons. Like Breake C, Breake CL performance exhibits the same trend with viscosity reduction over time and measured until viscosity is at or below our target point of 10 centipoise. Next, we will look at Breake CL's performance in a coiled tubing system. This information can also be found in our AAD conference paper that Mark mentioned earlier. We had the opportunity, if a customer came to us, had a polymer-based solids-free system was used for drilling laterals via coiled tubing. was assessed with respect to the potential to remediate reported damage. Operations suspected excessive viscous leak off during drilling of the horizontal intervals as the cause of damage, as recent production did not achieve programmed rates. Specifically, the concern was invasion of a solids-free coiled tubing system into the producing formation either as whole fluid, filtrate, and or filter cake, where the filter cake likely formed close to the toe. TBC-Brinadd was asked to evaluate the incorporation of a breaker into the coiled tubing system to be used during drilling that would remain inert and subsequently degrade the viscosity of any residual whole fluid, thus improving initial cleanup of the well and alleviating the perceived damage. The required period to delay viscosity reduction for this solids-free system was established using previous horizontals, including a safety factor, and determined to be 40 hours. This graph shows rheology measurements versus time for both high-end 600 RPM readings and low-end readings at 6, 3, and 0.3 RPM readings, respectively, for two controls versus selected coiled tubing systems. Two coiled tubing systems were built, with one incorporating Ultra Breake M and the other incorporating Breake CL. This data shows the presence of Ultra Breake M exhibited negligible decrease of their low ends and nil decrease of the 600 RPM over 40 hours. It was found that the pH of the coiled tubing systems averaged around 11 after 40 hours and was too high to allow the activation of the Ultra Breake M over time. The coiled tubing system that incorporated Breake CL, which has a higher peroxide and active oxygen content, exhibited the most relative decrease of the three low-end readings, as well as the high-end, when compared to the controls and to the other coiled tubing systems. When compared to the rheology of the base, 6% KCl is the purple line, the low-end readings for this coiled tubing system after 4 hours are nearly equivalent. Breake CL generated an effective delay mechanism when incorporated into this brine-based, solids-free coiled tubing system at 165 degrees F. Thus, it was a candidate for use as a delayed breaker for field applications at lower temperatures. Breake CL promoted greater than 90% degradation of the low-end rheology as compared to the initial viscosity measured at ambient conditions. Introducing our Breake RC, which is our reduced calcium peroxide. It is an alternative to Ultra Breake M, which generates approximately 5 to 7% active oxygen. Its reduced assay allows it to be classified as a non-oxidizer. It is also stable with storage and has an active oxygen loss of less than 1% per year. It will also disperse readily into water and brines, and the pH ranges approximately 8 to nearly 12. Typical application ranges from 200 to 300 degrees F, and typical concentration ranges from 0.25 to 2 pounds per 1,000 gallons. Next, we will see Breake C's performance in a cross-linked fluid. Same guar setup of 25 pounds per 1,000 gallons was utilized. Temperature application for this was 250 degrees F. The Breake RC concentration was 3.5 pounds per 1,000 gallons. Breake RC's performance provides viscosity reduction over time and measured until viscosity is at or below our target point of 10 centipoids. An effective break was reached within 75 minutes. Next is the liquid suspension Breake RCL. It is a suspension of calcium peroxide based in the same environmentally friendly synthetic fluid used for Breake CL. It is classified as a non-oxidizer, and it is available in 1 or 2 pounds per gallon concentrates. Typical application range remains the same, 200 to 300 degrees F, and the typical usage concentration range is 1 to 5 gallons per 1,000 gallons. Now we will show you the Breake RCL's performance in a cross-linked fluid. Here we're testing it in another 25 pound per 1,000 gallon guar, 11.8 pH, 250 degrees F. The Breake RCL's concentration was 2 gallons per 1,000 gallons. We had a customer requirement for a break profile that would be achieved around 2 hours. Above, we were able to provide stable viscosity over time, with the break performance occurring at the requested time period. Introducing our magnesium peroxide product line, Ultra Breake M and MG. They are available in two sizes. M is the powder and Mg is the granular, again developed to reduce dust hazards seen in the field. Alkaline magnesium peroxide is used as a delayed breaker for drilling and stimulation applications. It will improve or has been proven to filtrate removal and drilling and completion operations, especially at temperatures less than 109 degrees F. And it's activated by temperature or a mild acidic solution. Typical temperature ranges dependent upon drilling is from 70 degrees F to 235 degrees F. In stimulation, it ranges from 200 to 300 degrees F. Usage concentration in drilling is 0.5 to 2 pounds per barrel, and in stimulation is 0.25 to 2 pounds per 1,000 gallons. Next, we have Ultra Breake's performance in a Slickwater fluid. This testing is from the same paper from the AAD mentioned earlier. And the preparation of these Slickwater fluids were sheared at the same RPM of 1,000 RPMs for 30 seconds to produce the slick water. It was then placed in the rheometer cup and then a 400 PSI was applied. Four stages were again repeated, 5 minutes simulating pumping, 30 minutes simulating velocity in a fracture, 60 minutes for shut-in time, and then the final 10 minutes to give our final viscosity. The slick water fluid with Ultra Breake maintained viscosity during stage 2 at the 40 reciprocal shear rate, while providing brake performance with 80% viscosity reduction compared to the baseline, and only required 0.45 pounds per 1,000 gallons usage concentration, as opposed to the others that were at 2 pounds per 1,000 gallon concentration. Next, you will see Ultra Breake's performance in a Crosslinked fluid. Here, the testing temperature was 275 degrees F and a 25 pound per 1,000 gallon guar. Usage concentration for the Ultra Breake was at 4 pounds per 1,000 gallons. The Crosslinked fluid with Ultra Breake maintained stable viscosity over time at 275 F, with brake performance occurring near the 2-hour mark. Ultra Breake's performance now in a drilling fluid, and its impact on drilling fluid's viscosity, especially at the low shear rate viscosity point of 0.3 RPMs. When looking at drilling fluids, the 0.3 RPM allows us to have a measurable tracking of the peroxide's impact on the viscosity of fluid over time. The 0.3 RPM is an indicator for the viscosity of the fluid to be able to suspend the bridging agents and drill solids. In the top table, we have two drilling fluids, thick cell ultra systems, one with and one without Ultra Breake. Fluid with Ultra Breake has 1 pound per barrel of Ultra Breake and 1 pound per barrel of Thermosol A, which is our oxygen scavenger. Looking at the low shear rate viscosity initially, over time up to 160 hours at 3 temperature designations of 100, 150, and 190 F. We have stable viscosity profile over time, which is what we want to see. It remains inert within the system and is only activated once an acid is applied within the filter cake. The bottom table in images is of a 9.7 pound per gallon drilling fluid with a lubricant, a starch for fluid loss, and a xanthan for viscosity. One system has the internal breaker Ultra Breake, and both included a 2% by volume of simulated drill solids. The images show residual filter cake after acid soak and flowback. The image on the right is the Ultra Breake shown and enhanced the cleanup over time. And thank you for your time today. I will now hand it over to Kimberly Dobson to conclude the webinar.
Thank you, Kim and Mark. And thank you all for joining us. We've really enjoyed the last few weeks in providing a new way and a new platform to bring our product and technology to the world in the mix of the coronavirus. As Mark had mentioned, we do have our AADE paper, and there's other publications located on our website. Our technology webinar series, the replays, can also be found on our website at the following URL at the bottom. We've covered a wide range of products, product technologies, and also our offerings at TBC over the last few weeks. We do customize all of our fluids to meet our customers' requirements and certain specifications. If you have any questions or comments, feel free to post in the chat section or down below. You can also reach out to your sales and marketing team at salesandmarketingtbcbrinadd.com. Thanks again for your time.